All right. Hello, everyone. Good morning. My name is Mengu Sukan. I'm here with my advisor, Steve Feiner. And this is work done with our co-authors, Carmine Elvezio at Columbia University and Barbara Tversky at Teachers College. So our paper's title starts with providing assistance for orienting 3D objects. I want to start by giving a couple of examples of why you might want to orient objects in certain ways, other than, of course, for fun and games. One domain where you might need to orient an object in a certain way is visual inspection. Imagine you're holding a product and you need to find its expiration date, or you need the inventory number or a serial number from a piece of equipment. It might not be a big deal just to search for it if you're doing it doing it once, but what if you need to do it many times over and over, for example, in a warehouse on different types of objects? So the question we're trying to answer here is, if a computer could recognize and track the object you're holding, how would it show you what direction you need to turn it and by how much to get the right perspective? Another domain where you need to hold objects in certain orientations is assembly, because parts usually only fit together in certain ways. Assembly manuals typically show illustrations of how the various pieces fit together, often with added annotations such as arrows or callouts to communicate an action. These can be helpful, but note that our starting configuration often looks much different than what's shown in the manual. Again, we can ask the same question. If a computer could recognize and track the pieces to be assembled, how would it show us how to orient the pieces so that they fit together so that we can save time and prevent errors? In this paper, we present a set of interactive rotation guidance approaches. During our exploration, we've designed and implemented 3 visualizations that follow common ways of thinking of 3D rotations and task assistance, along with a novel 4th visualization, handles, that was not very obvious in the beginning, but turned out to be the fastest and most preferred technique in our formal evaluation. As I said a moment ago, following assembly instructions from a manual can be challenging for a lot of people. In fact, there are standard tests that measure how quickly and accurately a person can perform mental rotation. It turns out that the scores from these tests can vary greatly from person to person. And so the main point I'm trying to make here is that a large portion of the population could benefit from assistive technologies for tasks that would otherwise require mental rotation, like assembly. There is much previous work that we drew inspiration from. We described these in detail in our paper, and here are a few representative examples. As we already mentioned, people have been relying on printed instruction manuals for a long time, and people have come up with a set of best practices on how to design the most effective paper illustrations. There's a body of work on how to represent and execute 3D rotations on 2D displays using 2D input methods such as mouse and a keyboard. When we come to 3D user interfaces, we have a number of projects that have explored how to guide users to move their body in certain ways. For example, to learn how to dance or perform martial arts by projecting directly onto their body, like in this example, or sometimes using an augmented mirror. For maintenance and assembly, we have many projects that rely on augmenting physical equipment with virtual copies of the individual pieces that animate to illustrate an action. For example, how to open a door and remove a filter. Typically, these animations are not interactive, however, meaning they show you what you need to do, but don't track your progress to keep updating to correct you if necessary. There's a collection of work that rely on ghost copies to show you where to place your next piece in an assembly task. Much of this work has been conducted using Legos, with only a small discrete set of positions and orientations. Lastly, there's work that use interactive annotations. In this example, we have a 3D curved arrow that shows how to perform a rotation task and changes color in real time to indicate the magnitude of the remaining rotation. Note that this particular rotation is also constrained to only a single degree of freedom because of how the one piece rests on top of the other. So we build on this work by exploring how we can guide users interactively while performing an unconstrained, in other words, 3 degree of freedom rotation task. Before we go into the individual visualizations, I want to quickly go over our setup. Given that we're trying to aid users with orienting handheld objects, it made sense to have our users wear a head-worn display so that they have both their hands available for holding and rotating the object. When considering different types of head-worn displays, we decided to focus on monocular displays like Google Glass that are lightweight and untethered, which can be more easily worn in industrial settings. There are a number of such displays, such as the Recon Jet and Vuzix M300. As you can see in this inset, which we photographed directly through glass, the field of view is small, which means that we can't rely on registered overlaid graphics like we would have done if we had a wide field of view stereo head-worn display. So taking this into account, we render our visualizations on top of a virtual copy of the task object. Just as a quick note, though, that this is not a requirement for any of our visualizations. In fact, I have with me a running version that uses regular registered AR on a video see-through tablet that you're welcome to try after this talk. Just to finish up on the logistics, for tracking we used an external camera and a marker-covered object. The tracking information was streamed to the device over Wi-Fi. And for our task object, we chose an object that looked like one of those abstract shapes from the mental rotation test that I showed you earlier. Before we talk about the design decisions that went into each of our visualizations, let me just show you a brief preview of what it looks like for someone looking through glass. This is handles, the novel technique, which I'll explain at the end, that ended up working the best. Okay, so here are our interaction techniques. Let's start with one that we call the most geek-friendly one, single axis. A well-known property of 3D transformations is that the rotation required to transform a 3D body from any orientation to any other arbitrary orientation can be represented by a single rotation about a unique axis. If you've done any 3D programming, this should sound very familiar. So being geeks ourselves, this is the first visualization we developed and tested. Here we visualize the axis as a cylinder and the direction of rotation by a series of curved arrows. The amount of rotation is encoded in the angle that the arrows span, which means that as the user performs rotation, the arrows disappear one after another until they're all gone, at which point the object itself turns green to indicate completion. So let's see it in action. In this example, we're carefully and slowly rotating the object. Although you can't see it here, the user is holding it with two hands because the axis of rotation is an awkward one. And by awkward, I mean that it cuts through the object at a weird angle. So I'm going to play it one more time. Note how the axis updates in real time to reflect that the rotation that is performed is not perfect and shows corrective action in real time. Just to give you a sense of the amount of design and thought that went into making the visualization in the form that you just saw, here's an early prototype that we presented as a poster at last year's ISMAR when we just had started the project. Unfortunately, we don't have enough time to go into details here, but I just want to quickly mention that we put a lot of effort to make the arrows as clear and easy to interpret as possible. We describe and justify these decisions in much more detail in our paper. Okay, so let's move on to our second visualization, Euler. People often find it easier to think of a 3D rotation in terms of a series of rotations along the three major axes of an object. You may also know these angles as yaw, pitch, and roll. Before we implemented this, we also thought that it might be advantageous because it should be easier to perform these rotations along these major axes of the object. So here you can see that we have the same style of arrows that we use for optimal axis. So there's a ring with arrows attached to each of the major axes of the object. The order which is important is encoded by traffic light colors, red, yellow, and green, and the user is persistently reminded to pay attention to the order with the numbers 1, 2, 3 on the right side of the screen. So this is what it looks like in action. Notice how we're first collapsing the red arrows and then the yellow, followed by the green. And similar to, let me play that one more time. And similar to single axis, the arrow tips always face the camera. Okay. So this is our third visualization, Animate. While discussing the previous work, we talked about ghost copies and animation as tools that have been used in the past for conveying an action that needs to be performed. We wanted to try those two techniques in our context. Here we have a virtual representation of the tracked task object, which is opaque. Additionally, we also have a transparent ghost copy that animates to the target orientation. This animation runs in a loop, always starting at the current orientation. Similar to optimal axis, there were some subtle settings that we thought were important to make the animation as clear and easy to understand as possible. Again, please refer to the paper for a rationale. But I'll highlight it in the video just in a second. This is what Animate looks like in action. Notice how the ghost starts from the current orientation and animates to target orientation. I'm going to play it one more time. Also notice a short pause between the loops and how the frequency of animation increases as we near the target orientation. Okay, and here's our last visualization, handles. While we were thinking about how else we can visualize a rotation, we noticed that another way to do this would be to highlight a point on the object, for example, a landmark like a corner, and tell you that you need to rotate the object such that the landmark is now at a different location. Of course, when you're rotating an object about its center, a single landmark is not enough to constrain 3 DOF rotation because you have one more degree of freedom. So we actually needed 2 points. So we came up with this early prototype. Here you have 2 control points that are rigidly attached to the object, meaning that the user controls their position by rotating the object itself. And each of the control points has a corresponding target point that is fixed in space. And the user's goal is to rotate the object such that both control points coincide with their corresponding target points. We liked how this felt in our early tests, but there were a couple of issues. First, the points were hard to see, especially on small field of view devices. And 2, depending on how we picked those points and the desired final orientation, sometimes the target points ended up in places that were hard or impossible to see, for example, behind the object. Here's what the final version of handles looks like. We replaced the control points with handles, which make it easier to understand that those points are rigidly attached to the object and can be moved by rotating the object. We replaced the control points with small rings. Looking at the bottom image, you can notice how the ring shape benefits from occlusion as a depth cue, which is especially helpful on a monocular display to clearly display that, or to clearly show that the handle is going through the ring. We came up with a heuristic to ensure that the rings are always positioned at the same location in front of the object and along the horizontal center line of the screen. And last but not least, we included a set of arrows to trace the path of each handle that is required for the correct alignment, which you can think of as a cookie crumb trail. So this is what handles looks like in action. Notice how the final alignment near the end is done against a stable and easy to see target, which is different from previous visualizations. I'm going to play it one more time. So to evaluate the effectiveness of our designs and to get qualitative feedback, we conducted a user study. We recruited 17 participants, 9 of them female. It was a single session within subject experiment where each user completed 4 practice and 16 timed trials for each one of the 5 techniques. I say 5 techniques because we added a control condition that I'll describe in the next slide. As our independent variable, we measured task completion time. To ensure the same level of accuracy across users and conditions, we implemented an acceptance threshold. As the users got within 8 degrees of the target orientation, they had to hold it there for a second for the system to accept it as the correct answer and load up the next trial. This threshold 8 degrees was based on pilots. And we had the system generate a random axis for each trial, but we didn't want too small or too large rotations to affect our timing data, so we had the system randomly choose between one of these 4 angles. I mentioned that we had a control condition. So our control condition had a static target on the right, and we tracked the tracked proxy that was controlled by a user on the left. This is analogous to seeing the final pose on a paper manual and trying to figure out how to rotate it mentally and executing the rotation. Before we conducted our study, we came up with 5 hypotheses that I summarize here. So we hypothesized that handles will be fastest, it would be most preferred, and it would be fastest for fine-tuning. When we say fine-tuning, we mean that the amount of time the user spends when they're almost done, but not quite there yet. For this analysis, we defined it to be 16 degrees, twice the size of our acceptance threshold. And because we had 5 hypotheses, we used a Bonferroni adjusted alpha of 0.01 for all of our analyses. Here are the results. This is task completion time, so smaller numbers, shorter bars are better. Overall, handles was significantly faster than the rest of the techniques, which confirmed our main hypothesis. When we broke the task into ballistic versus fine-tuning steps, we noticed that handles and animate were neck and neck for ballistic, the orange bars. But the reason that handles ended up beating animate in overall time turned out to be the improved fine-tuning time, which is the gray bars. Again, this confirmed another one of our hypotheses. Other notes are that Euler ended up taking the longest, which makes, I guess, sense because you have to interpret and execute 3 separate rotations. As expected, static took a long time, especially for fine-tuning, where we had some participants get stuck, which by that I mean they thought they were finished with the rotation. That is, the target and the control looked the same to them, but in reality they weren't, and the system wouldn't go on. So they lost some time trying to get it in place. Here are the results from our qualitative feedback surveys. For these charts, one is best, so having more votes towards the left of the chart is better. You can see that handles trended to being most preferred pretty much across the board. And single axis actually trended to be the least preferred. In fact, Eulerian single axis generally ranked lower than static. In other words, some people preferred to have no instruction compared to having either Euler or single axis. There were some people who ranked static as their favorite. Anecdotally, we conducted a post-hoc interview with one of the participants who ranked static as her preferred method. And she said that it was easier for her to just think about the rotation by looking at the target orientation without any of the clutter. She had a perfect score on the mental rotation test. So one takeaway here is, I guess, that future interfaces like these have to be cognizant that users require different levels of assistance. Future work, we want to port these to wider field of view stereoscopic head-worn displays with overlaid visualizations. In fact, part of that is, as I mentioned, already done. We can do that on a tablet. We want to be able to support translation and constrained rotations. And we would like to actually define a common interface for interactive task assistant widgets so that we already did this with these visualizations, such that if you define a target orientation and a source object, we can keep changing the visualization. But it would be nice to have a public interface so that other the widgets developed by other researchers, we can share with them and they can share with us, and we can build compound widgets together. In fact, to this end, we're actually building a Unity framework that we're going to release in a few months. So if you're working in this area, please actually let us know, and we'd love to share our framework with you. And that's it. So before I take any questions, I just want to mention again that I have a running version with me. So if you'd like to try them out, please find me after the talk. I'll also be around during WIST. So thank you for listening.
Questions for Mengu? Very nice talk.
Thank you.
In lunchtime, block of questions. Can you comment a little bit more about how you chose the locations for the handles?
Right. So I mentioned that one of the problems with the earlier versions was that based on the location, based on that choice, sometimes the targets ended up behind the object. So our heuristic was that we really locked them to be in front. So we determined where they need to be at the end, such that we back calculated where the handles need to go, so that at the end of the rotation they'll end up in the front. So the handles are always in different locations of the object, but the targets are determined by us, essentially.
Understood.
Thank you for your presentation. Apologies if I didn't catch it during your talk. I didn't quite get the motivation for this. So the system will show you how to rotate the object?
Mm-hmm. Right.
And what sort of situation are you seeing this working for?
So we were saying, for example, you're holding something in your hand and you need to know where the expiration date is, right? So it could be here, it could be there, it could be anywhere, right? So one way to do that right now is I can just keep rotating it until I find it, right? Which can be time consuming if you have to do it over and over, for example. But if a system can track the object and knows where it is, it can just show me, oh, you need to rotate like this. So I just perform that rotation. Here's my expiration date.
Okay, so this makes the assumption that the system has some knowledge of the object, and
yes,
that it is also, the system can imply what you want to know at the specific time. Is that correct?
Yeah, so as input to the system, we have a tracked object and we have a target orientation. So the system knows what the target is.
All right.
And another example I gave earlier was when you want to assemble like two things together. For example,
that
right.
one I got it. Okay. All right. Thank you very much.
You're welcome.
Another question.
Sure.
It's actually related to what I was asking about earlier with respect to sort of the locations of the handles. Do you think it would make sense for the handles to not to protrude from natural places?
Right. So again, in our one of our earlier prototypes, just took the major axes of the object and extended them. So I think depending on the situation, it might make sense to highlight natural landmarks. But again, I think you would be best suited to pick one such that at the end of the rotation they face forward. That was one of the critical reasons, I think, why it ended up winning at the end in terms of being fastest.
Any other questions? Let's thank our speaker again.
Thank you.